I feel that it's quite appropriate that today's word is fervent, because I believe you said one meaning was bright and shiny, and radium is bright and shiny. Marie Skłodowska, born in Warsaw in 1867, was the daughter of a secondary school teacher. Who knew she was destined to become a physicist and chemist, famous for her pioneering research of fervent radioactivity? In 1891, Marie moved to Paris to continue her studies in physics and mathematics at the Sorbonne. While there, she met Pierre Curie. They were married in 1894. She became who we know her as, Marie Curie. The discovery of radioactivity by Henri Becquerel in 1896 inspired the Curies. They went on to research and analyze radioactivity, which led to the isolation of polonium, named after Marie's birth country, Poland, and radium. Marie Curie developed methods for the separation of radium from radioactive residues in sufficient quantities to allow for its characterization and careful study of its properties, particularly its therapeutic properties. Alas, because of her work with radium, Marie Curie contracted aplastic anemia, a condition where the bone marrow doesn't provide enough cells to replace the blood, and she died in July of 1934. She was 66 years old. Marie Curie gave the following presentation, which I will be presenting, about the discovery of radium on May 14, 1921, at Vassar College in Poughkeepsie, New York. I could tell you many things about radium and radioactivity, and it would take a long time. But as we cannot do that, I shall only give you a short account of my early work about radium. Radium is no more than a baby. It is no more than 20 years old, but conditions of the discovery were somewhat peculiar, and so it is always of interest to remember them and to explain them. We must go back to the year 1897. Professor Curie and I worked at that time in the laboratory of the School of Physics and Chemistry, where Professor Curie held his lectures. I was engaged in some work on uranium rays, which had been discovered 2 years before by Professor Becquerel. I spent some time in studying the way of making good measurements of the uranium rays. And then I wanted to know if there were other elements giving out the rays of the same kind. So I took up work about all known elements and their compounds, and found that uranium compounds are active, and also all thorium compounds. But other elements were not found active, nor were their compounds. As for the uranium and thorium compounds, I found that they were active in proportion to their radium or thorium content. The more radium or thorium, the greater the activity. The activity being an atomic property of the elements, uranium and thorium. Then I took up measurements of minerals, and I found that several of those which contained uranium or thorium, or both, were active. But the activity was not what I could expect. It was greater than that for uranium or thorium compounds, like the oxides, which are almost entirely composed of these elements. Then I thought that there should be in the mineral some unknown element having a much greater radioactivity than uranium or thorium. And I wanted to find and to separate that element. And I settled to that work with Professor Curie. We thought it would be done in several weeks or months, but it was not so. It took many years of hard work to finish that task. There was not one new element, there were several of them. But the most important is radium, which could be separated in its pure state. Now, the special interest of radium is its intensity of its rays, which are several million times greater than that of uranium rays. And the effects of the rays make the radium so important. If we take a practical point of view, then the most important property of the rays is the production of physiological effects in the cells of the human organism. Good results have been obtained in many cases. What is considered particularly important is the treatment of cancer. The medical utilization of radium makes it necessary to get that element in sufficient quantities. And so, a factory of radium was started to begin with in France. And later in America, where a big quantity of ore named carnotite is available. America does produce many grams of radium every year, but the price is still very high because the quantity of radium contained in the ore is so small. The radium is more than 100,000 times dearer than gold. But we must not forget that when radium was discovered, no one knew that it would prove useful in hospitals. The work was one of pure science. And this is proof that scientific work must not be considered from the point of view of direct usefulness of it. It must be done for itself, for the beauty of science. And then there's always the chance that a scientific discovery may become like radium, a benefit for humanity. The scientific history of radium is beautiful. The properties of the rays have been studied very closely. We know that particles are expelled from radium with a great velocity near that of light. We know that the atoms of radium are destroyed by the expulsion of these particles, some of which are atoms of helium. And in that way, it has been proved that the radioactive elements are constantly disintegrating, and that they produce at the end ordinary elements, principally helium and lead. That is, as you see, a theory of transformation of atoms which are not stable, as was believed before, but may undergo spontaneous changes. Radium is not alone in having these properties. Many others having radio elements are known already. The polonium, the mesothorium, the radiothorium, the actinium. We also know radioactive gases named emanations. There is a great variety of substances and its effects in radioactivity. There is always a vast field left to experimentation, and I hope that we may have some beautiful progress in the following years. It is my earnest desire that some of you may carry on the scientific work and keep your ambition, determination to make a permanent contribution to science. Mr. Toastmaster.